I'd like to uh, make an application of these magnetic ideas that we were introduced to on Monday. And some of this information you'll need for some of the homeworks. I was anticipating showing you some of this stuff in lecture today. So instead, I'll give you this video, and I've extended the due date for the homework that was due tonight out till Friday. And so hopefully you can view this, get some ideas about something called a velocity selector, so you understand what that is. It's a piece of equipment that does exactly what the name implies. It selects a velocity, but you need to know the context. What velocity of what's it doing, how's it working? So it's a great application of magnetic fields and electric fields. So let's start. Let's begin discussing the topic of a velocity selector. And what you're selecting the velocity of is atoms or subatomic particles, perhaps molecules. Right, so these are things about the size of an atom or smaller. These are very small masses. And you can understand we're talking about charges with electricity, and charges are protons and electrons, so they're small. And to do experiments to examine the theories for how the forces of nature work on these particles, you have to be able to control the motion. We've been studying the motion of things right from the beginning of the course. We started talking about how a force applied to a mass makes it change its motion and accelerate. Newton's second law, F equals ma. We've talked about motion graphs, and we've talked about when things are in motion, they can collide. And all these things are true with things like cars and people and throwing footballs and billiard balls bumping into each other. And but it also applies to small masses like protons and electrons and neutrons. And as we move into this world of electricity and magnetism, the particles that we use to test these theories are typically small, very, very small. And how you control the motion of very small particles becomes an issue. It's not like you can put an engine on something and press the gas pedal and get up to a certain speed and then just, control it that way. You have to go through some extra machinations to control the motion, the velocity, or the acceleration of very small atomic or subatomic particles. And we use this thing called a velocity selector. It's in your book. We'll use this device. You'll see it now in this part of the course, electricity and magnetism. You'll also see it at the end of the course in the part of the course that talks about quantum physics. Again, talking about nuclear physics and atomic particles that are small. So as far as pedagogically, it's a device that uses lots of the ideas that we've been talking about. And it's just a clever use of the ideas. So it's a good example of what people have been able to come up with. So here's the idea. So let's say we want to do an experiment where we have a proton. Let's say we get a proton, and we want to do an experiment on a proton, and we want to test the motion of the proton in the presence of a magnetic field, for instance. Well, first we have to get a proton, and then if we're testing magnetic field, we know that we have to have some motion. The proton has to be in motion. So the way we get a proton is we put some material in an oven, and we heat up the oven, and if we get things hot enough, we can start getting what's called a plasma. And a plasma is where we start separating the subatomic particles, the protons and the neutrons and the electrons. We start pulling things apart. We could get a hydrogen atom, which just has one proton in its nucleus, and we could strip away its electron, and then we could get a proton. So anyway, we need some heat to get a proton. But the problem with heat is when things get hot, they begin to move very rapidly. One of the relationships in physics is that kinetic energy increases when temperature increases. Things move faster when they're hotter. When things are cold, they move more slowly. When they're hot, they move more quickly. And when you put a bunch of atoms in an oven, you get particles moving at all different speeds. They have a broad array of speeds, different velocities. But I would like to be able to have just one particular velocity. I'd like to know the velocity of the proton as it comes out of this oven. So what we do is we make a hole in the oven where a proton, so let's say a positive particle, is going to come out the hole, right? And that's just a random event. There are lots of protons, and one just happens to find its way out the hole in the bottom. And it comes out. It could have a large array of velocities. It could be fast, could be slow. And I want to be able to just filter or select only the protons that have a particular velocity. So what people do is they make a capacitor. Here are the plates of a capacitor, which are placed outside the oven and forming kind of a path or a channel that the proton would come through. And so this is my Q, it's a positive charge, and it has some velocity V as it comes out the oven. And then I'm going to put charge on the plates of a capacitor, because that's just what we do. We put charge on capacitors. That's what we do. And we know that when I have the plus and the minus arranged like this, there's an electric field formed. And the electric field is going to point in the direction that a positive charge would want to go. Well, a positive charge is going to want to go in this direction. So the electric field is going to be from left to right. So there's E. And since the particle that I'm using from the oven is a positive charge, when it enters this area between the plates of the capacitor, it's going to want to travel to the right. So its path is going to be like this. It's going to arc over towards the negative plate and away from the positive plate. Now, at the bottom of this device, this velocity selector, I have a wall with a hole in it. Now, my desire is to get this this proton to not arc over in any direction, but to come straight down and go through the hole in the bottom. This is the V selected, the velocity that's selected by the machine. When a proton has the correct velocity, it will not have a trajectory that's arced towards the negative plate. It will instead come straight down through the device and come out the hole in the bottom. And you look at this and say, well, there's an electric field and a charged particle. It's gonna shift to the right. It has to. That's correct, until I put another field in here. I put a magnetic field in here, and the magnetic field is oriented perpendicular to the page. So in this case, we want the magnetic field to be pointing out from the page. So I'm going to fill this whole area here with magnetic field. I'm going to make a magnet. And there are going to be B fields pointing out of the page. And it's going to fill the entire area. Now, the B field is going to fill this entire area between the plates. And I'm just showing a couple of vectors, but I want you to understand that the B field fills the whole area between the plates. The E field fills the whole area between the plates. They're perpendicular to each other. And if you use the right-hand rule, I have a positive Q moving down. So QV is down. So point the 4 right fingers of your hand down. Your palm should be pointing out of the page, and your thumb will then be pointing to the left. So if that's the case, then I have an electric force to the right, and I have a magnetic force to the left. And the goal of my velocity selector is to reach equilibrium, where the electric force to the right and the magnetic force to the left are opposite and equal. And then we have an equilibrium situation, and the charged particle has 0 net force on it, and then it will travel in a straight line and come down through the plates of the capacitor, through the hole in the bottom of the device, and out into this region down here, where I set up some other equipment to do my experiment. So the first part is to get the charged particle from an oven, then send it through the velocity selector, which is the crossed electric and magnetic fields. So there's a magnet and there is a capacitor. And then at just the right velocity, the proton will come through the device without being deflected. Will go through the hole in the bottom and comes out with a very well-known velocity, the selected velocity. So here are the principles. We have a magnetic force and an electric force. They're opposite each other. Equilibrium is the condition for selecting a velocity. And so what that would look like is this. That would be F magnetic minus F electric equals 0. Okay? One direction is positive, one is negative. I'm saying the magnetic field direction, the magnetic force direction is the positive direction. Left is positive, right is negative. So our F net, this is equal to F net. That's going to be 0 because it's equilibrium. So what that says is the magnetic force equals the electric force. Here's where we have to look up some other equations. The electric force equation, you know this, electric force divided by QF equals the electric field. So if I rearrange this with algebra, I can say electric force is E times QF. And my magnetic force, we just learned this the other day in class, and I'm going to use the scalar equation, is Q times V times B perpendicular, so that the B has to be perpendicular to the QV. Well, the geometry of this problem, the B field is designed to be perpendicular to QV. So it's just going to be QVB, and this is a QF. This is a field charge. And notice that I have a QF on both sides. They cancel. If I divide both sides by QF, they disappear. Then I get VB equals E. And if I solve for the velocity, this will be the selected velocity, because this is the velocity that creates equilibrium. equals E over B. So the velocity selector chooses a velocity according to the ratio of the electric field and the magnetic field. And I'll leave it for you to prove to yourself that the units work out to meters per second. Okay. I don't think we discussed this in class the other day. Let's discuss momentarily here the units on magnetic field, B. Our equation is, look at this, force magnetic is Q times V times B. If I do units, that's newtons equals coulombs times meters per second times B. Now, I'm going to do a little sleight of hand here because the way I've written it here is not going to show the typical units on B field. Instead, I'm just going to take the seconds here and I'm going to slide them underneath the coulombs. So if I just do a little sleight of hand here with the units, I get newtons equals coulombs per second times M times B. And a coulomb per second, hopefully you recognize that. If you've got your page in your notebook where you have all the units, you should recognize that a coulomb per second is an amp. That's the unit of current. So I'm going to rewrite it in terms of that. So Newton equals amp meter times B. If I solve for B, that'll tell me the units of B. B equals Newton per amp meter. Those are the units of magnetic field. Okay, so everything in this box is units. It's not equations of variables that I'm solving an equation. These are just units. I'm just doing math and algebra with units. All right. Otherwise, you're going to think these are brand new equations that you have to memorize. These are not equations that you're going to solve problems with. These are just looking at units. This is dimensional analysis. And a Newton per amp meter is called a T. Now we're going to have real trouble because T has been used for tension in the past. It's also been used for period when we talked about repetitive motion. So now we have T for something else. Now it's a unit. T equals a Tesla for Nikola Tesla. All right, that's the unit of magnetic field, the Tesla. It's a Newton per amp meter. It's the units on B. It's the units on B field, magnetic field. Okay, so the units, the B units, are newtons per amp meter or Tesla. Write that down somewhere in your notebook. And now you got to remember that a capital T, when it's a unit, refers to a Tesla. Okay, so you should be able to put those units into this equation right here. And you know the units of electric field, newtons per coulomb, and work the dimensional analysis and prove to yourself that it comes out to be meters per second. And you're going to have to use bunches of composites and do dimensional analysis just like I showed you down here. You're going to do some equations in algebra on units. And you should prove to yourself that it comes out to be meters per second. That's a good little exercise for you to do on your own. Okay. So that's a velocity selector. So when the homeworks talk about velocity selector. That's what it's talking about. Let's do a couple of other things here that'll be helpful as a prerequisite or a precursor for Friday, so we don't have to go through quite so much material because we missed today. Here is a bar magnet. South pole here, North pole here. And then we have a wire loop. And hopefully you can see the 3 dimensions here. The wire loop is oriented perpendicular to the magnet so that I could push the magnet through the middle of the loop. And the loop is a solid loop. It's like a necklace. It's a solid loop of wire. There's no battery connected to it or anything else. It's just a loop of wire, copper. And it's a round loop, and I can push the magnet through the middle. And if I grab the wire loop and I move the wire loop this way, this is my velocity v. I'm grabbing the wire loop and I'm moving it to the right over the magnet. And we're going to talk about magnetic forces in this problem. And the first thing you have to realize is we're talking about the kind of magnetic force that's represented by our equation QV in parens with a vector sign over it, cross B. This is what we talked about the other day. And in order to talk about this kind of magnetic force, this is magnet moving charge force, then I have to identify where are the charges, what's the direction of the velocity, and what's the direction of the B field. Those are the questions you need to ask yourself, as I'm going to show you a lot of examples of this magnetic force principle, and those are always going to be the things I'm trying to show you with the pictures. But if you don't know that, or you're not clear on what I'm trying to show you, it's going to be very confusing. So I'm going to draw physical diagrams, and those physical diagrams are supposed to help you identify these 3 vectors, these 3 things. Charge is not a vector, it's a scalar, but there have to be charges, there has to be movement, and there has to be a B field. Well, in this problem, the charges are on the wire. Wire is just packed with charge, positive charge. Wire just holds all kinds of charge. So whenever we have a wire in a problem, you can just know that there's tons of charge on that wire. All right. It doesn't have to be hooked to a battery or anything else. It's just a phenomenon of the wire. Lots of charge on the wire. And now I'm telling you that the charges are moving to the right. So QV is to the right. Positive charges are moving to the right. QV is to the right. Now we got to do the B field. Well, we said the other day that the B field, the maps of B field are, I'm going to make them square instead of round because it's easier to talk about things that are perpendicular. The B field comes out the north pole of a magnet and then goes in the south pole. And it's up here, it's down here, it's up here, it's down here. Okay? Well, I've got B field all over the place in all directions, so I've got to focus on only certain parts of the problem. I don't care about the B field that's over here at the North Pole, because the wire loop where the charges are, right? This wire loop, that's where the charges are. That's where the magnetic force is going to be. That's over here on the south side. So I don't care about magnetic field over here on the north side. So I can ignore all of the B field information over there. I only care about B field that's over here on the south side. Okay? Well, I have B field pointing in here at the South Pole, and I have it pointing left up here at the top, and I have it pointing left here at the bottom. Okay? And I have it pointing up here, and I have it pointing down here. So I still have a lot of different directions for the B field. Which ones matter? Well, remember, cross product means two things: right-hand rule and only perpendicular matters. Well, if QV is horizontal to the right, perpendicular is going to be up and down. I'm only interested in B fields that are up and down. Well, here's a B field that's down. Here's a B field that's up. Those are the only B fields I care about. I don't care about the B fields that are horizontal here at the South Pole or up here above and below the magnet. Those are parallel to QV. I don't care about those. They don't contribute to the magnetic force. But I do have a vertical B field here, which is down, and a vertical B field here, which is up. I need to look at each of those separately because the direction of B is different. At the top of the wire loop, the B field that matters is pointing down. At the bottom of the wire loop, the B field that matters is pointing up. I need to use my right-hand rule on both of those in order to figure out the forces on the charges that are on the wire loop as I move the wire loop over the South Pole to the right. So let's do this. QV is to the right. Let's do the bottom first. Let's do the bottom part of the wire loop. Okay, we're looking now at the charges that are down here at the bottom of the loop. Okay, the B field is up. QV is to the right. If you do your right-hand rule, 4 right-hand fingers to the right, palm pointing up, your thumb of your right hand should be pointing out of the page. Out of the page. So the magnetic force is out of the page. This is F magnetic. If I do at the top of the page, the B field is down. QV is to the right. Palm is down. My finger is going into the board. So that's going to be like this. F magnetic is into the page. And since this is a perspective drawing, into the page is going to mean like this. Out of the page is going to mean like this. Charges are going to move. At the top, they're moving in this drawing to the right. At the bottom, they're moving to the left. Into the page, hopefully what you can see with this perspective drawing, this part of the wire loop back here is behind the page, and this part of the wire loop here is in front of the page. This is a perspective drawing. I know my three-dimensional things are not the best, but you got to be able to see that this part of the wire loop is in front of the magnet. This is the part behind the magnet. So when things are going into the page at the top, they're going from in front of the magnet, the part of the wire that's in front of the magnet, towards the part that's behind the magnet. That's into the page. And at the bottom, where they're coming out of the page, they're coming from behind the magnet to in front of the magnet. That's this way. And hopefully what you can see is that there is going to be a clockwise rotation of current around this wire loop. As I move this wire over the South Pole to the right, there's going to be what's called an induced current. The current is charges moving on the wire, induced current flowing clockwise. In this diagram, the way I'm looking at the wire loop, it would flow clockwise. We've made a generator. This is a simple generator. I've created current flow without the need for a battery. There's no battery here. There's no 12-volt battery, 9-volt battery, 2-volt battery, 3-volt battery. There's no battery. But I'm getting current to flow because of this magnetic force, this QV cross B. So I can get current to flow on a wire just by moving it near a magnet. Okay? And this is the process, the procedure for figuring out which way the current would flow. Okay. Once I get the wire loop over the middle of the bar magnet, not at the end, but over the middle, so it's sitting right in the middle of the magnet, notice that the B fields in the middle of the magnet are left and right. They're horizontal. There is no vertical B field near the middle of the magnet. The only B fields near the middle of the magnet are horizontal, and that's parallel to QV. So what that says is the current, the induced current, would stop when the wire loop got to the center of the bar magnet, because the QV and the B are parallel, they're not perpendicular. If I kept moving the wire loop to the right and pulled it off the north side of the magnet, then there would be, again, perpendicular B field, and I would get a magnetic force, and it would be the opposite direction. The induced current would flow in the opposite direction from what we've got here on the left side when the wire loop was over the south pole. As it's moving to the right over the north pole, it's going to reverse the current flow. And so, in essence, I've created an AC current. It's going in clockwise direction when it's near the left end of the wire loop moving to the right, and it'll flow in a counterclockwise direction as the wire loop gets pulled off the north pole of the magnet on the right-hand side. And I encourage you to draw that and prove it to yourself. Redraw the diagram with the wire loop near the north pole moving to the right, and convince yourself that the current will flow in an opposite direction. It'll flow counterclockwise. Okay? All right. So now, let's talk about another example. I have a bar magnet. South here, north here. I have a wire loop, again, same kind of a deal. And now I'm going to tell you that the magnet is flowing or being moved to the right or to the left. That's the velocity of the magnet is moving to the left. That's what I'm telling you. Instead of the wire loop moving, I'm moving the magnet to the left. Hopefully what you can see is that QV is still to the right, because my equation demands that the motion has to be the charges. I have to think in terms of the wire loop moving, because that's where my charges are. I've told you the magnet is moving. You need to redraw the problem so that the wire loop is moving in such a way that it's producing the same kind of relative motion as it does when I tell you the magnet's moving to the left. Well, if I hold the magnet still and move the loop to the right, that would produce the same relative motion. Convince yourself. You just have to think about that a little bit. This is our first foray into relativity and frames of reference. It's all just context. And I've always told you, context is kind of arbitrary. When I tell you that the magnet's moving to the left, then I'm telling you my context is that the wire loop is stationary. But when you have to apply the equation and do the right-hand rule, the equation dictates that the context be that the magnet is stationary. All right, so QV is to the right. Again, we have South Pole and North Pole, and so we still have our B fields, which are the same as before. So that hasn't changed, okay? Again, I'm only concerned with the B fields near the wire loop and only the B fields that are perpendicular to the QV. And so we're going to get the exact same result we had before. It'll be the exact same result that we had before. It'll be out at the bottom, in at the top. This is current, right? F magnetic is into the board at the top, and F magnetic is out of the board at the bottom. And we get the exact same situation. All right? Okay. All right, how about this? Physical diagrams are going to be very important to get the geometry straight as we do these problems, because direction is important and context is important and B fields are important. We got 3 dimensions instead of 2. So your physical diagram and drawing the physical diagram correctly is going to be a more important skill on this stuff than it ever has been in the past. If you haven't been drawing physical diagrams in the past and maybe you got away with it, I don't think you're going to be able to get away with it now. You're really going to have to start drawing physical diagrams. Otherwise, there's just too many ways you can get it wrong. So here's the next thing that I want to talk about, and that'll be it for this lecture. Here's a wire, and here's a wire. Okay, and they go on. You know, they're very long. Okay, I'm just showing a piece of the wire, and here's the end of a bar magnet, and this is a top view. I'm looking down from on top. So it would be as if I had 2 long wires sitting on the desk in front of me, and I was holding a round bar magnet, and I'm looking at the top of the round bar magnet. And let's say that top is the North Pole. Okay, so that's a top view. Looking down, I see the magnet in the middle and the 2 wires running along the table. A different perspective would be if I did a front view. So if I got down and put my eyes level with the tabletop, I would see this wire sitting on the tabletop, this wire sitting on the tabletop, and I would see the bar magnet above the 2 pieces of wire. This is the North Pole that was facing up in my top view. This is the South Pole facing down. And I'm going to drop the magnet through the wires. Oh, come on. So I'm going to drop the magnet through the wires. So where are the Q's? So let's see here. The Q's are on the wires. Always, always, always charges on the wires. I'm telling you, in my context, I'm telling you that the magnet is falling down. But that means that the QV is up, because the equation demands that I have a context where the magnet is standing still. And to get the same relative motion, I'd have to then have the wires moving up towards the magnet. We have our drawing of the B fields. B fields come out the North Pole and go in the South Pole. So they come out the North Pole, go in the South Pole, and there and there. These are the B fields. I'm only interested in the B fields that are close to the magnet and perpendicular to QV. So I'm only interested in the horizontal B fields that are close to the wires where the Q's are. And again, I need to do right hand rule. Point your four fingers of your right hand up. Let's do the left hand wire first. Point your palm to the right, and you should find that you have a magnetic force going into the page. On the left-hand side, you point your four fingers of your right hand up, point your palm to the left, because the B field's to the left, and you should find that the magnetic force is out of the page. And that would be current flowing on that wire that way and on this wire this way. And I'm marking a different drawing because it's easier to show the direction of the current flow on the top drawing than it is on the bottom drawing. The bottom drawing, it's easier to see the direction of the B fields. Okay. So let's see. This is a top view. That tells you, when I say top view here, I'm telling you where my eyeball is. My eyeball is above the magnet looking down. Okay. When I say front and back, let's put a few. This is the front. This is the back. This is the right. And this is the left. So when I say front view, that means that my eyeball in the front view is over here. My eyeball is in the front, and now I've moved my head down so that I'm looking from the front, okay? And the top is up here. This is top. All right? And I'm looking at the wires edge on instead of at their length, so I'm looking at their edges. And instead of looking at the edge of the magnet, I'm looking at the length of the magnet when I go to a front view. Okay, so this is a front view. My eyeball is in the front. So as we do these diagrams, I know a lot of these things are going to be unfamiliar, but they're not terribly complex. It's just you have to think about them. Where you're looking and how you're looking at things matters. If you want to get orientations and directions correct in order to do right-hand rules and vector directions. And the physical drawings are going to be extremely important to be able to understand the drawing and understand what's going on. So anyway, if something's unclear, let me know. Hopefully this is helpful, and enjoy your day off, and I'll see you on Friday.